I am looking at problem number 8 on the HL paper 1 from November 2022 from your mock exams from last week. So I'm going to start with problem number 8. Here we have the line L1 that has a position vector given, as well as L2 has a vector equation. So you can see here highlighted in yellow, this is the general form for a vector equation of a line. So R is the line, and A is a point, a position. It's the position vector of a point that the line runs through, and the direction vector is B. So what we want to do here for L1 is, one way to think of this is to rewrite this R as in this form. So we could write it as R is equal to the position vector of a point. So that's the constant terms right here for -1 and 9, plus some variable lambda, or in this case p, times the direction vector, which are the coefficients of p here, 3, 2, and 1. Imagine if you were to just distribute that p back in, you multiply that vector by the scalar p, then we'd have 3p plus, or over 2p and 1p, and then adding that to 4, -1, 9, and we can just add those positions, and that gives us 4 plus 3p, -1 plus 2p, and 9 plus p, which is our original vector. So I just wanted to show you that we just sort of took our original vector and broke it into parts to help us see this equation of a line in vector form. So we could do that for the second vector as well by just writing our constants. In the first vector, that's the point, some point -2, +1, and +1, plus q times the coefficients of q, 1, -1, and 2. So that's just a helpful way to think about this. Now, to find the points of the coordinate M where these two lines intersect, we can set the two lines equal to each other and solve for P and Q. So ultimately, I'll just move this over here. And all that means, how would we solve this? We can just create a bunch of equations from this. Like we know that the first position in that top position would be 4 plus 3p would equal the top position on the right side, -2 plus 1q. And we could go to the middle position, -1 plus 2p equals 1 minus q. Here we have two equations with two unknowns. We could go ahead and do the third row as well, but we don't need to because we have two equations and two unknowns, so we should be able to solve. And in fact, notice I have positive q and negative q right on top of each other, so I could just add these two equations together right just as they are. So I'm going to go ahead and do that. And that results in positive 3 plus 5p equals -1 plus 0. And we can now solve for p. So 5p equals -4, and p equals -4 over 5, which is -0.8 if you want to use the decimal form. And now we have found the value of p. We can take that and substitute it into one of the original equations to find q. So let's just go with the top equation. 4 minus 3 times -0.8 equals negative 2 plus q. And when you simplify the left and add 2 to both sides, you get that q is equal to 3.6. Now we have, that's not quite our final answer. We have p and we have q, but to find the point where they intersect, we need to take either of those values and substitute them in to find the specific point. So we can just actually, I guess we didn't need necessarily both equations. We didn't need both q and p, but we can use, I'll just use p and the first equation, or the first vector, 3p plus 4, but in place of p, I'm going to do negative 0.8. 3 times negative 0.8 plus 4 will be my x coordinate. 2 times negative 0.8. I'm looking back at this equation right there. 2 times negative 0.8 minus 1, and p negative 0.8, let's see, plus 9. That gives us the position vector of the point where these two intersect, which is 1.6, negative 2.6, 8.2, and the point itself, which is what we're asked for, is the coordinates 1.6, negative 2.6, 8.2. And that's our answer for part A, the coordinates of that point M. Finding the acute angle between the lines, you have this equation in your formula booklet, and you may remember from when we did vectors, even though we have three component vectors, that still works the same. Our equation is that the cosine of the angle between two vectors is the dot product of those vectors. So I'll just write r1 dot r2 over, well, that's not quite right. It's the dot product of the direction vectors. I'll come back to that in a minute. Over the magnitude of the direction vectors. So the direction vectors, like I said back from this original equation, r equals a plus lambda b, the direction vector is b. And so our two direction vectors are they're basically the coefficients of the variable. So our direction vectors are 3, 2, 1 and 1, negative 1, 2. And so we want the magnitude of 3, or the dot product of 3, 2, 1. 1, negative 1, 2 over the magnitude of 3, 2, 1. That shouldn't be it. Fine. 3, 2, 1, 1, negative 1, 2. So to get the dot product, we just multiply each position by its corresponding position and add all those together. That's 3 times 1 plus 2 times negative 1 plus 1 times 2. And then the magnitudes are simply square root of 3 squared plus 2 squared plus 1 squared times square root of 1 squared plus negative 1 squared plus 2 squared. And when you simplify all of that, you get that cosine, well, I'll just go ahead and go straight to theta. You simplify it and then take the inverse cosine of that value, and you get that theta is 1.24 radians.